So it's a great pleasure to have today Oscar Reula as our speaker. So as usual, let me introduce a little bit the speaker. So he got his PhD from the University of Chicago in USA. And after that, he did a certain, let's say, activity as a postdoctoral, I guess, in Max Planck in Germany. And then in 1988, I think, yes, he went back to Argentina and to University of Nacional of Córdoba, where he spent essentially all his career together with CONICET, and he did all the, let's say, all the academic steps there. He also got several awards, and among them, one that really attracted my attention was in 2008, you get a Professor Partnership Award from NVIDIA, right? That was particularly interesting to see. And his expertise is in computational physics and, let's say, general relativity and partial differential equations, numerical methods for them. And today's talk is about that and is about new advances in the theory of hyperbolic systems with constraints. Oscar, the floor is yours.
Thank you for the invitation. It's really great to be here. I'm teaching a course for 2 months, so I'm around. Okay, maybe. Or hola, hello, yeah. Okay. So I'm teaching a course here for 2 months, so I'll be around. So if anybody's interested in talking about their fields, what they are doing, etc., I'm happy to listen and try to collaborate. So that's the idea of coming here. So today, I'm going to talk about some long program that we have been pursuing with Fernando Ábalos and David Hindlich for several years now. And this is trying to understand hyperbolic systems as they appear in physics. Namely, they appear like equations with constraints and gauge freedoms. So we want to understand this because prior to these studies, the issue of whether some theory was well posed, namely that you could put in a computer and compute something that you can predict the future, was based in a lot of things you have to do. You have to fix the gauge. You have to get the constraints equation sorted out, get some evolution equation, then check some things, etc. And for doing that, there were many paths that you can follow. So it was not clear, for instance, if you get some result that some theory was not well posed. It was not clear that was because you failed to find the right reduction of the equations, or it was just that it was really ill posed. So we wanted to understand this, and this program is trying to understand both things, constraints and gauge freedoms, and how you can take a theory complete without worrying about these things and say, okay, this theory is well posed or this theory is not well posed. And so in the story, you have to take another theory, another model for doing the physics. So I'll go through some of these things today, trying to explain what is the tool that we have been developing to treat these things, how to check this well-posedness. There are some technical stuff that I don't want to talk, and most of it I don't even know because it's pseudo-differential equations, etc. Some techniques you have to use in the middle, and we are not going to use them. But there are the basic things that decides about the theories are some algebraic things, some linear algebra aspect of the theory. So this we can discuss and see and try to understand. So anything you want to ask or you don't understand, just ask me, and we have the time to discuss and go slow, okay? So this is hard to see from here. So the idea is this, as I was mentioning, just given a theory, and I'm thinking, for instance, some higher derivative theories of gravity, for instance. There is a zoo of possible theories, and you say, okay, I have the theory, has Riemann tensor derivatives some this combination, this product, etc. Is that model okay, sound? Can I predict something with this? And so the general path to that is very complicated. You have to fix gauges, constraints, etc. So we want to find some way of just saying that directly, just looking at the algebraic aspect of the theory and check that, okay? So this is the idea. So if the theory that you are proposing has no constraint or gauge, then the answer is well known, and is this concept of strong hyperbolicity, right? So your theory is like time derivative of something equal to some derivatives in space of something, and you check the metrics that is multiplying these things, whether this metric has some properties, and if that metric has some properties, then you know that your system is well posed. If it doesn't, you know that it's ill posed, and end of history. So that's what you want to reach at some point. So we want to understand the general case when you have the constraints and gauge, and in general, in this case, you don't have this setting where you have time derivative of something equal to space derivative of something or nothing else, right? It's more complicated. So in general, you have many more equations, and you have some equations which are redundant, so in the sense that they are equations which have, because of the gauge, they have kernels. So you have an equation, a system of equations where you put something, and it's identically zero. That will be a gauge. So as I say, there are some parts which are difficult and some parts which are easy. So we are going to go through the sort of easy part and avoid going to the mess of the proof, because that's important. The other way is how to get a proof of things, some theorem, but it's not really basic. So this is the outline of the talk. I'm going to talk about the setting. I'm going to come like here, I think. A setting, some introduction, and some examples. Restrict to constant coefficients system, because that's the easy part where we know everything. And then we are going to talk about the theory when there is no constraint or gauge. And this is a theorem by Kreis metric theorems. And a variation of this theorem introduced by Avalos, which is a new, this theorem has 4 equivalent conditions, and this one introduced a 5th equivalent condition. So we are discussing a bit this one. And then we are going to see what happens when we have constraints, okay? And here we'll put also some examples. And then at the end, once we know all these things, we'll discuss necessary and sufficient conditions for well-posedness for the whole system. And we finish with some questions and some partial answers we have now. So the setting is this, is first-order quasi-linear system. So there is a variable here. This alpha index is an A index are usually a set of tensor fields. So this is a set of tensor fields that goes to another set of tensor fields. And this is a space-time index, A. And this is a derivative, a covariant. Any derivative is okay, because if we have some connection, etc., we push it in this side. And this is a source that depends on you. So K and J depends on you, and these are the system. In general, you can put the system in first order. It's a mess, but you can put them like that, and it's easier to analyze them as a first order system.
So the U's can be also on the right-hand side?
Yeah, yeah. This J is a function of U, so anything.
But J doesn't contain derivatives, right? I'm here.
Oh.
J doesn't contain derivatives.
No, only U.
Okay.
So the only derivative is here. So this is why it's quasi-linear, because the derivative enters linearly. Of course, if you have a theory, say a second-order theory, where when you write it down, like Einstein's equation, you have first derivative of the metric, but those are new variables, and so here you will only get derivative of the first derivatives, which are all other variables. So this is the equation index. So this maps variables, field index, to equations, right? So this is the equation index, and this is the variable index. And in general, what we will have is usually that E is bigger than F because there are constraints. Sometimes this is equal because you can have gauge in this side and gauge in this side. But we are not going to talk about gauge today. We are going to talk about the constraints. So in that case, this is going to be bigger than F. And if it equal, it's because there is no constraint. So this difference is the number of constraints in this case, okay? And there is later we're going to see that there is a good definition of what a constraint is. It's very nice definition, actually. So this is well defined, these quantities, okay? And it has, this definition is very nice and has some consequences. The known theory, that is a mathematical theory that for well-posedness, is when there is no constraint. So that the index here is, so the number of variables is equal to the number of equations, right? So the dimension here is the same dimension than here. So this is for each space-time index here, this is a matrix, right? A square matrix. So for instance, electromagnetism is a theory with constraints. You have these two equations, which are time derivatives, and then you have these two equations which are constraints because they involve derivative at the same time. So if you were going to give data E and B at some t equal to 0, then you have to satisfy at t equal to 0 these two equations and then solve these two. And on before, if you take a time derivative here and use the equation, you get that the time derivative here is 0, provided that the time derivative of rho is minus the gradient of J, the divergence of J. So this current conservation. And if you take the time derivative of this, then you use this equation and you get the divergence of a rotor and it's 0 of a curve. So you know that if they initially are satisfied, they are satisfied under evolution, and you take this as evolution equations. And this is for some slicing of the space-time, right? These are part of the tensor, the Maxwell tensor that you used to write as E and B instead of antisymmetric tensor, right? But this is by no means trivial that you can split this in here. For instance, I could add to this equation times some vector field, so that this is a vectorial equation, this is a scalar equation, but I can take a fixed vector, any vector, multiply this and add here. And that will be equivalent. So there are many evolution equations which in the constraint manifold they are the same result, the same solution, but you can change the nature of the equation by just adding things here, and that can happen. So here another example, you have a linearized Einstein's equation in the ADM formalism. So you have, this is the linearized metric, the metric perturbation. This is the linearized extrinsic form. And you have this equation, which is just a definition of this. And you have a time derivative of this. And here I have two second derivatives. So this is not of the form that we were talking before, but to see what we are going to do later. And these are the constraints, a scalar constraint and the vector constraints. And this n here is the density size lapse, which we write as some determinant of this h to some power times q. And q is a given quantity. So q is given in this equation, some function of space and time. So to treat this system, instead of writing it as a first order system with a lot of all these variables entering in the game, etc., a big system, we do something else, and it's the following. We go to Fourier space, so the H components go to a Fourier space. These are the Fourier transform components. The derivative goes to IK, and we introduce this other quantity here, which is a two tensor, which is IK times HMN. And so now the equations in terms of this cell are first order. There is only linear in K when you use this, because this will have a K here already, okay? So this I think this shouldn't be K twiddle here. These are unit vectors here only. So when you write the other system that we have before, this one becomes just this system here. So we have this matrix. And then we analyze this metric. And what we do is the following. We introduce what is a pencil matrix. For this case, this matrix is just the identity and zeros. So it's the identity here for these two tensor and this identity here. This identity here in the diagonal of this 2 by 2 block. And then these are the space case here, all right? So this is the, all this, okay? So this is a system now in Fourier space, and you make a Kronecker decomposition of this pencil. This is something I'm going to tell you what it means later. But when you do it, you find that you get this matrix. So you have here a block, a square block, which has these lambdas here. So if you look at the eigenvalues of this, is lambda equal to 0, lambda equal to 1, lambda equal to -1, and lambda plus minus square root of b. Remember, b was this thing here, this. And then you have this bunch of terms which have a lambda and a 1, lambda and a 1, etc. And they are called the L1 blocks in the Kronecker decomposition way of looking at the things. And so immediately from here you can say, okay, this system is well posed when b is different from 0. When b is equal to 0, the decomposition is not like that. It has a 1 here. And then we know that this is a Jordan block, 2 by 2 Jordan block, and we know that the system there is ill-posed. Okay. And this was a system that was used numerically at the beginning of general relativity. People use the system, just this system would be equal to 0. So it was ill-posed. They were having problems. And finally, people realized that it was ill-posed. And in fact, numerically, they could see that there was something wrong. They could study that there was something going wrong there. And it was this case, that there was a 1 here. So it's a mild degeneracy, but at the end, it spoils your code. So from this Kronecker decomposition, you get this, and you can immediately see that the system is either well-posed or ill-posed. And this has to do with the constraints. Yes?
You said when b equals 0, it suddenly picks up a 1 there?
Yeah.
So what something singular happens at b equals 0? How did it jump? If B is very, very small, there's no 1, and B becomes 0 and suddenly becomes
Well, it's
1?
the decomposition changes. The metrics relating to the composition changes. When you have this equal to, what happens is following. When you have this equal to that, this metric can have, and suppose there is something here. This metric has 2 eigenvalues when these 2 are different. So I have 2 eigenvectors. And so I can decompose and diagonalize. If these 2 are equal, I could have only just 1 eigenvector. And then the decomposition picks up here a 1. It's convention to put a 1. It's anything but not 0.
I see. Okay,
So you
thanks.
lose one of the eigenvectors. That's the thing. So whatever you have in the block, in the square matrix, this is the Jordan decomposition. And the Jordan decomposition tells you if you get something diagonal, your metric is diagonalizable. If you get some block with some 1 or would be bigger blocks, then you know that this metric is non-diagonalizable. And the exponential of that metric, which is what it enters on all this, is it grows badly, even when the eigenvalues are imaginary. So this, I want to convey this. Once you know, once you do the Kronecker decomposition, say, okay, this is the block which is okay, contains the physics, and these are the constraints, are 4 of this L. And what we are going to do is to change this one here, a couple of them, into more equations which have this property, which are blocks like this. In fact, they are going to be one-dimensional blocks, these 2. I think I don't have it. Yeah, so this is the result. For B equals to 0, it's not well posed. There is a 2 Jordan block. For B equal, different from 0 is well posed. And the constraints are also well posed. You can see this in a generic way. But the reduction that we are using here to see all this, reduction means what are your, here I didn't introduce the term yet, but what are your evolution equations? You have a big equation, a reduction is picking some evolution equation from the system, okay? So reduction is a matrix, basically. But the reduction here is only pseudo-differential, and that means that when you try to write it down, it depends on the K. So it's a reduction in the Fourier space, not in the physical space, okay? So then you say, what happens when I have a matrix that depends, a system that depends on the field and on the position, etc. You just cannot use Fourier space, and that's okay. I cannot use it. But you can do the calculus fields and are nonlinear. And this is pseudo-differential calculus. And the idea there is that what you are looking for ill-posedness is the limit K going to infinity. It's a high frequency, high energy limit, say, in physics. And in that high energy limit, you are looking at smaller and smaller neighborhood of points. And you have to be sure that these neighborhoods are okay. And so when you are doing this localization of the problems, then the problems becomes trivial, constant coefficients locally, and so you can apply this. So it's this limit what is going on there. But it's hard to do mathematics with the idea of the limit. You have to do the real calculation and those things, and that's complicated. So we are not going to enter in this. So here is a reduction. So you have this system here, and you want to introduce another matrix here, so that this index goes from the space of variables to the space of variables, and get a reduction, okay? This is going to be our evolution system. For the system of Maxwell, were the first 2 equations. So you put an H that kills the 2 constraints and evolve this. For the system for linearized gravity, also you get the 2 evolution equations, you kill the rest. So here now you have, oh, maybe it's because it's the Zoom. I see it. Okay. These reductions are not unique, as I say, because you can add the other equations to this one and still get a system, and in general they are consistent. So the solutions for the when the constraints are satisfied are the same. So this is not unique, and there are many ways of doing this. And in fact, the way we do this for proving things is using a pseudo-differential H. So this H is in Fourier space, so here I have a K, and this H depends on K. Doesn't change. Okay. So now we have this, and so the question is now, given this system above, when does it exist a reduction that will make this system strongly hyperbolic, well posed? So this is, as I say, well, the procedure was get some H, try, get another H, try. When you get one that works, then try to see that the constraints are evolving correctly, etc. So it was a try and an error with huge equation was really painful. And now we know that this is not needed, basically. So we want to see whether we can prove something without going through this process, just finding a reduction that will do the things once and for all, and in a simple way. So here is, this is a particular reduction. You just take these two equations here. And here, but let's see how we can do this with this Kronecker decomposition. You go to Fourier space, look at the Kronecker decomposition of Maxwell, and you find this. These are the real degrees of freedom, lambda equal to plus minus, so 2 degrees of freedom with the speed of light in one direction, in the other direction. This is for some fixed case, say this one. And these are the two constraints, since that comes the 2L ones here. And this is the linear combination that takes you to this setting in Fourier space when you take the n to be this one and the k to be in the z direction, okay, in the third direction here. So this is a reduction. You take this metric, multiply by this, and you get a system which is okay, where the eigenvalues are these ones. And so what you do here, this metric, what it does is to take one of these and put it like this. So there will be a lambda here minus A, and the other one, lambda here minus B. So these are why you have these two here. Right? So this is a reduction. This reduction we do in Fourier space. In physical space, you can only do it for A and B equal to 1, which is the one that I showed you before, just killing the constraints, okay? But in Fourier space, we can do better. We can do that, and so we can put anything here. And this, in the system, these are the propagation speeds of the waves. So that means that you can put any speed, any speed you want to these constraints, because these are propagation of constraint. They are 0 initially, and they will be 0, but for the whole system, they don't know. They evolve, right? And if they were not 0, they will be evolving with these particular speeds. And they are not physical, because the physical solutions are the ones that satisfy the constraints, and they are 0. But in general, you have these propagation speeds. And so, in a way, you can get to these things doing something which is called extension of the system, or divergence cleaning, for that people use in the, for instance, in magnetohydrodynamics. And this is put in an equation that will take the constraint and evolve the constraint, okay? And this is good because if the constraint there is sitting in a nonlinear theory, it can happen that the noise will start accumulating there because the constraint is not moving. So there will be noise and the constraint will start growing. And you will get to some growth in the inside the solution you are interested because the constraint is sitting. While if you put to it some velocity, then this noise generated by the constraint will move away from your grid and you will get a nice solution. So this is important in the technical aspect of simulations. Yeah, that you are able to give some velocities to the constraints. So let me give you now the theory when you have a reduction. So now once you have a reduction, the system is a n by n system. So you have as many equations and variables, and you have some time derivative of something equal to something, okay? So let me tell you when a system is well posed in this sense. Because we are not. So you have your system here. We apply some reduction and get a system. I think I didn't. Yeah, consider this to be alpha, say, this index. It's just already so. The reduction is taking place. So this is wrong. So you take a slicing of the space-time and vector to do the time translation, the time evolution. You split the identity this way with this. This is a projection in these surfaces. And so you use it to get the equation like this. So the 0 term here, in the n direction, you take it this, you assume that this is invertible, and you take the inverse here and multiply the inverse here, and these are the a's. Huh? In general, why I'm saying this? This is wrong. We already have a square system, and we are assuming this. So I don't know why this is here, but our system is square already. So this is there is an assumption here that this is invertible, and we will come back to this later. But we assume, at the moment we assume that. So the connection is written in the time direction and the space direction, and so we get this system, right? So time derivative is equal to something else. So we go to Fourier space. So the space derivative go to k's. So you substitute this by ik, and you write the solution in Fourier series. Here I'm using Fourier series. Could be the Fourier transform. Doesn't matter. These are these values once you know the u. And then you apply the equation, and you get this equation, which is a linear equation. It's an ordinary equation, huh? Linear. So the solution is just this one, where you have to take the exponent of p. And so if you are given a data here, say to a finite sum, then the solution is this one, right? And there is no problem, this converges because the sum is finite. This, in the end, is a result, you can think of the Cauchy-Kowalewski theorem. That's a classical theorem that says if your data is analytic, so that this thing is finite, then your solution is analytic, so this is finite, so it's analytic. And he has a big theorem, they have a big theorem like that. And that theorem dominated the theory of partial differential equations for many years. They say, no big deal, not big deal. I have analytic data, I get an analytic solution, that's it. I can do series, etc., whatever I want. This is nice. But the problem is that when you try to say, okay, I don't only want to get a solution, but I want to get a solution that if I change my initial data a bit, the solution changes a bit. If I don't have that, I could make a mistake in my measurements of 10 to the minus 8, doesn't matter. If I don't have continuity, the equation between the one without errors and with errors could be totally different. So we lose predictability. We cannot predict, right? It's like what happens. It's different, but it's like what happens when one say, okay, the weather I cannot predict for more than 10 days because the equations start departure. This is another problem, but this is worse because in cases where the system is not well posed, you can find an initial data here and a sequence of initial data that goes to this one at t equal to 0, but the solution goes to infinity at any time when you approach this one. So it's pretty bad. It's really something very, very bad about the equations. So this theorem is not good. It's a mathematical theory, it's true, but it's not good for physics or anything that you want to predict what happens. And this was something that Hadamard, I think in the 20s, realized that we don't have continuity from the data to the solution. And say, okay, there is a problem here. And so after that, the theory of elliptic equations developed, and then the theory of symmetric hyperbolic system developed, the real theory, where you have to say more. Then you can show this is a theorem that says the system is well posed so that you have continuity if and only if the norm of this metric, the exponential, is bounded independently of k. So you can take k as big as you want, but this exponential has to be bounded, right? Remember, k going very big is going to high frequencies, and I don't want the high frequency to change my system, so I want to bound these things. And the proof is, the if is easy. You say, okay, I have my solution, the norm in the L2 norm. I have the solution in the Fourier space. I have this Plancherel identity here between the norms in Fourier and in space and Fourier. Then since I have this bound here, remember that this was e to the p with respect to the f, which is the initial data. So if this is bounded, I just bound by this times the norm of f. So I get this thing here. And this, I use Plancherel again. I go to the physical space and say, okay, this is bounded by c times f squared. And f is the initial data. The only if is not very difficult. You have to find some sequence of k's and f in the initial data such that the sequence is bounded by 1. You just say take something which is, the norm is 1, and such that this thing is L, right? And L is an integer, so when you go into the sequence, this goes to infinity. And so you lose this. And this is not difficult to see. You put some high frequency in the right place, in the right eigenvalue that you are losing, and you get this, okay? So this is important. So this tells you when the system is well posed, okay? you might say, okay, what happens if your system is nonlinear and has many terms and there is u to the 15,000 that kills because I have minus sign and so on? No. You can show that if you have a system as we had before and you have the A there, the K, if this fails, even the system, any system will fail, right? No matter what you put in U and how it depends on A, etc., all the system will fail. Because again, you can do your perturbation very small in space, but very high frequency, and you go into the limit where the perturbation is smaller and smaller and smaller. So you take a fixed wave number for the perturbation, but increase the frequency so that the wave number goes to 0. And so you have the same solution scaled down, smaller and smaller, and the solution blows away, okay? So you can do this localization at the same time blowing. And so it's easy to see that if that fails, your theory is pretty bad. You cannot recuperate it. So now we have to see this thing here, when this thing is bounded. And this exponential, the way you compute the exponential is say, okay, I take my matrix A, this is the P in the other one, take Q and diagonalize it if you can, or make it a Jordan block, diagonalize it in Jordan blocks with Q to the -1, and the exponential of this is just exponential Q times the exponential of this metric. And this is easy to compute. And this lambda matrix is just K times, these are unit vectors only, some blocks, these Jordan blocks. And the Jordan blocks are like this. So it has the same eigenvalue in the diagonal and have 1 over the diagonal and then zeros, right? So it's lambda L to the identity matrix plus this matrix. This is called delta, this metric in this case. And you could see that this metric, if you have n rows or columns here, and you take the n's, I think the n plus 1 power of this delta, that gives you 0. So in the end, the exponential of this block times k is just this thing. So you get this thing times a finite sum, a polynomial in k, right? And the only way that you don't get a polynomial if this metric if these blocks are unit, right? So the metric is diagonalizable. If these blocks are unit, so are one-dimensional, then you don't get this sum, you get just this one, n equal to 0 here. So this is a case where if lambda is imaginary, this thing is not going to grow. All other cases, you will have growth, right? So that tells you that what you need is that the metric be diagonalizable and the eigenvalues has to be imaginary, okay? That's the condition. So now we have a theorem in that sense, and this is a Cray theorem that says the third one here, this says there exists an S, so this was a Q, such that this thing is diagonal. It's a diagonal matrix with real eigenvalues. This real is because, remember in the formula I have an I because of the derivative. So sometimes I say imaginary, sometimes I say real, but not complex in general. So this third condition is the condition that we were saying that implies this here. And you can, so you have, you can show that this implies 3 and vice versa, right? So if and only if. All these are equivalent. Then there is another one which is very important. It says there is a positive definite metric, H, that might depend on K, such that this combination, this contraction here in the alpha, is symmetric in these two indices, right? And that would give you is an energy estimate. It says that there is some energy that you can bound. So this energy, these norms I was discussing here, for a system, I can use the norms that come when I have a system that come from this H. What happens is the H, again, is in general, is in the, depends on K, so these are in Fourier space, and then can be promoted to operators in space-time. And those are what you use to get an energy estimate. So estimate the norm of the solution with respect to a norm of the initial data. And you do it with this H. This is the right norm to do it. If this H doesn't depend on K, then you say that the system is symmetric hyperbolic. Then the energy is an energy that you can write down as an integral. And this is a system that appears in most of the physical systems. So electromagnetism, general relativity, fluid, whatever you want is in the setting of symmetric hyperbolic system. But this setting is, not all systems are symmetric hyperbolic. There are systems which are strongly hyperbolic, but not symmetric hyperbolic. And when you try to do this theory of reductions, etc., it's better to work in the bigger case. For instance, you can have a system which is symmetric hyperbolic, but when you want to treat the constraints in some way, you end up having a reduction that makes your system pseudo-differential. You need the case, right? The same for the constraint evolution. If you have a system, a reduction, then you will get a system which you evolve that system, and then you can prove that the constraint that is the remaining equation, if some integrability conditions satisfy, they are going to evolve in time. If they start to being zero, they keep being zero during time evolution. Right? This is also a theorem in general. But to prove that, in general, what you show is that the constraint system satisfies some evolution equation in themselves. And these evolution equations sometimes are strongly hyperbolic and not symmetric hyperbolic. So if you want to prove something there, you have to go to the strongly hyperbolic. So this is mathematically, this is the big thing where everything works. In physics, in many of the systems we have, you will have only the symmetric hyperbolic. So this H here, it doesn't depend on K. But it's a smaller set of theories. And then there is this condition here that says, okay, you take the inverse of S minus I minus lambda, take the inverse. And remember, we say in this case that this A has real eigenvalues. So if I take a complex here and I run it, then this is, when complex, this is going to be invertible because the eigenvalues are real. But what we can see is that if we take the imaginary part to 0, this blows up like K over 1 over the imaginary part. And not bigger than that. And let me show you, I think I have an example here of this condition, because with that condition, we will get another condition in a moment. So this is an easy way of seeing it. So take a 2x2 system. This is a pencil, Si minus the metric. The metric is this one. These are real, and this is a K. If K is 0, this is diagonal. And so the theorem holds. If K is different from 0, we should get something different. So we compute the inverse, and we get this one. So here you have 1 over lambda 1, 1 over lambda 2, but here you have 1 over lambda 1 and 1 over lambda 2 in the denominator. So if you take lambda 1 equal to lambda 2, so that the system is degenerate in this, then you will get, depending on whether the K is here or not, you will get, if the K is 0, you get 1 over lambda S and 1 over lambda S, so you will get well, I put it here. When this goes to this, the system goes to that. And you see, these ones goes diverge linearly, and these diverge quadratically. So this, unless k is 0, you have a divergence which is quadratic. Right? So this is a way of checking where your metric is diagonalizable. You do this, and check that this blows like 1 over s squared instead of like 1 over s. And then you know this part. And this is something you can do easily in a computer. You can plot and see how it goes to infinity, right? So the fifth condition is this. It says that the singular values of a singular value decomposition of this pencil matrix goes to 0 at most linearly in the imaginary part. So let me introduce what the singular value decomposition is. You take a matrix P from one space, vector space to another, not necessarily of the same dimension, and you multiply this by 2 matrices until you get this form. So it's a diagonal here, and the rest is 0. And these two matrices are built with the eigenvalues, eigenvectors of this matrix, and the eigenvector of this matrix. And they are, they are real. They are the square or root of the eigenvalues of that, so they are positive and real, or 0. And you order them. The biggest one is this one, etc. And this decomposition is very much used. For instance, if you have this matrix, this is a matrix of zeros and 1, representing the letter A, and you do the singular value decomposition and take a few of the eigenvalues and set 0 the others, you get images which are blurred until you get to, say, to the 5th here, and you get most of the image. So with less information, you can capture some image, okay? And this is used a lot by filtering images, etc. And in artificial intelligence also it's used a lot to see what is the important part of a matrix. You might have a metric very big and say, well, what is the important part? You do the singular value decomposition and take the part. You take this part, and maybe they are big, these are very small, so you would set them to 0 and then do the opposite transformation and get the P back and use that one, okay? So I'm running out of time. So what happened in this case, if you see the example, is that when you look at the singular value decomposition of this matrix, there is one that goes like this. So when lambda 1 and lambda 2 are equal, and k is different from 0, this goes to 0, and you get an epsilon square. So it decays like epsilon square, goes to 0 like epsilon square. If k is different from 0, if k is 0, this goes to 1 and decays like epsilon, okay? That's the way it works. Here there is a proof, but I'm not going to. I'm running really out of time, so let me see. This is important. You have this system, remember, and you say, okay, I will have a constraint if there is a metric here with a space-time index, or a vector, really, and an index in the equation. So this is a linear combination of equations such that when I take these two indices and symmetrize, I get 0. Okay? And this seems to be very strange. You say, why you want to do this? This is garage, which is very smart. So what happens is following. If you take a surface, this is a normal to the surface, you contract this with this, you will find that this part here doesn't have any derivative outside the surface, right? Because if there is a derivative outside the surface, there will be an n here, and so this will be symmetric with this other n, and that will give you 0. So this is a linear combination of equations that only have derivative on the surface. If you change the surface, you have another set of equations, we have the same property, right? Depends on the n. So this is what we want to call a constraint, because it's something that you want to do evolution, but has derivative in a surface. A surface which is constrained is not the one that you want to do the evolution. So those equations are not evolving; they're just in the initial surface and each slice, and you cannot evolve them, right? So that's why you call them constraints. There's no evolution. So constraints are well defined, are these C's, but the reductions not. So let me, well, this is how you do it for Maxwell. I will skip this, and the constraints of Maxwell, how you do, and the reductions and everything, but we don't have time. So let me go to the necessary condition. That's a result of Avalon. I think I'm going to stop with this result, which is really the important one. So now you have a system which is not square, right? I have more equations because I have these constraints. I have a system like that, and I say, okay, I cannot use this metric theorem of Kreis, because in that theorem, the matrices were square. But what about the singular value decomposition? The singular value decomposition is valid for all matrices, rectangular matrices. So it's not only for that. And then you look at this, and you can show this necessary condition, that when you take the singular value decomposition, all the singular values approach zero at eigenvalues at most linearly. So it's the same condition that we have the fifth condition. And this is valid for systems which are not square. What is going on? When the reduction goes through this procedure, and if it fails without the reduction, it's going to fail with the reduction. That's what you show. Right? If you have something like going like to zero faster, when you put the reduction, it's still going to go to zero faster. You know? So this way you just need to do the singular value decomposition of the big matrix without the reduction. So this is a condition that is independent of the reduction. And so you can check. You can get your system, do the singular value decomposition in Fourier space, and check this condition. And this condition fails, forget about the system. It's not well posed. I think this is the most important part of the result. So let me go. I will skip the proof of that, which is in different color because I was not planning to go through this. This was a reduction I already made. Let me go. Then there is the sufficient program, in the sense how you have a necessary condition, you want to see that it's sufficient. So you want to check that you have the sufficiency. And what you find there is the following. You do this Kronecker decomposition of the system, and you find the following. You have some blocks which are symmetric and positive. So these are the parts which are okay in the system. They are really the physical degrees of freedom of the theory. Once you check that these two evolve correctly with this condition of Avalos, then you get that equation, these are okay, and you have these terms here. This is the reduction we are going to put. This here. And I think I didn't put the metrics. And you have the L's. Here is an L2. Instead of being just this one, it's a big one, 2 by 3 matrix. And this is the thing you want to use as a reduction. You multiply these two things and get something like that. And then you play with the values of this constant until you get that this is symmetric and positive definite. And then you know that you have a reduction which is okay. So you show that you can make reductions for any system with constraints. So what we are now? Something on the sufficient program. In the physical systems, only these L2 blocks, these Gauge constraints are only L2 blocks. You can show this. So in physics, they seem to appear only these smaller constraints, the L1s, not the big ones, okay? So this is a point to have I didn't introduce some things. So this is the last slide. So we have a problem whether we have PDEs, but actually sometimes we need to go to pseudo-differential PDEs because we want to find these reductions which are general. Right? But okay, at the end of the day, what you want to prove is your system is well posed, and that you can have a reduction of the system which is pseudo-differential, doesn't matter. The end result is whether the system is well posed or not, independent of the equations you use to prove it. And there are several problems with this. When do you have causality for a strong hyperbolic system? For symmetric hyperbolic system, you have causality, you have Lycons, etc. For systems or whatever, you have Lycons. But for strongly hyperbolic system, it's difficult to do, to prove that things propagate causally. The smoothness of all this reduction, etc., is a problem, and you need for the proof these things. The quasi-linear case is hard, so we are dealing with some of these issues here. And then we have this extended system, divergence cleaning system that I say where you put some velocity to the constraints, add some equations. This now is mostly understood. We have a recent paper on this. We have an old paper and now a new paper, doing the things a bit different. You don't get most of the nice things of the old paper, unfortunately, but you get some understanding and some covariancy when you use these other methods. Constraint preservation in a covariant way, we understand this. There is a paper by Avalos and David Hindlich about this. And higher constraints, are there interesting examples? In physics, we don't find this higher order constraint, these L's which are big. But it will be nice to have some examples because the theory, the composition give you all these L's. These are all possible, but the physics doesn't care about them, just have only the first order one. So it will be interesting to see if there is some physical example. And gauge. Do we know about gauge? Yes. Gauge is well defined also. You can define in this first order system what is gauge in a very particular way. And we have now, when you have gauge, you have to extend your system. You have two things. Either you take some variables out and you say there are less variables. Say, for instance, if you take the metric, you say these components I take to be 1 because I have the freedom to do that. Or you can put more equations and say, I will put that the metric obeys a harmonic gauge condition. So there are two things. You can reduce your system, fixing some of the variables, or you can extend the system, right, taking more equations. So until you get a square system again, and then you treat it. So now we have a lot of progress in this, in understanding how to deal with this. And the gauge, in general, you see this, you have these metrics of L that were vertical. The gauge are the same metrics, but horizontal. So the way you do things, in the constraint, you can reduce a system or enlarge a system, and here you can also do the same, but the other way around. It's very pretty how they are, algebraically, they are related. We don't know why, but these are the cases. Okay, I'll stop here because I'm already over time.
Thank you very much. Time for questions.
So you never mentioned Lagrangians. Aren't Lagrangians useful for many of these things?
Not that I know. I know that there is a book that I couldn't read because it's quite difficult by Christodoulou, where he puts the Lagrangian and relates to symmetric hyperbolic system. But I tried several times to read it.
But things like having positive definite energy and things like that, isn't that related to what you're doing?
In some cases, yes. In some cases, the energy, for electromagnetism, the energy you get for proving stability is the normal energy. And an energy you build out of the equation by taking derivative, also time translation and using the Killing vector fields. So this you can do.
So is there an interesting system you know that is not described by Lagrangian that you're discussing?
Fluids.
We don't know the Lagrangian for this.
There is some sort of Lagrangian, but it's very strange in the manifold of trajectories. And then the dissipative system, like relativistic dissipative system, they don't come from Lagrange.
Thanks for the talk. It was very good. So my question is, you need to define these surfaces where the constraint equations are the same, right? So you define the surfaces are as perpendicular to some vector field you call T. So what can you do? What happens if this vector field has a torsion? So you cannot define these surfaces.
Okay. There are two things. First, in this system, don't know about metrics. Right? We are used to have metrics because we live in space-time. But here in this equation, there is not a metric. So the theory doesn't care about the metric. And in fact, what you get light cones, etc., but from the structure of this metric K, not from any metric. And so since you don't have metric at the beginning, you have surfaces, and you have a covector defining the surface, which is not a vector perpendicular. It's just, you say my surface is T equal to constant, and this covector is the gradient of T. And you move T, and the gradient is this. And then you have to choose a vector which is transverse, so that cuts the surfaces, to do the time evolution. Now, the question is, you see, we say at some point we need an N such that when you contract the N with the A and with the H, this thing is positive. Once you have an N where the things are positive, this N you can move it a bit. So you can choose the surfaces, say at some points, and then move the N a bit to glue them together. So since you can move the ends, they are not that unique. If they were unique, then you have problems because you cannot choose them, right? You suppose that the curl is not zero, they don't form surfaces. You have a flat tangent space, but they don't get together into a surface. That happens, for instance, for parabolic equations, where the N is fixed. The surfaces are fixed, right? The surface equal to constant of a parabolic equation is as fixed. And then you can make systems where this N cannot make surfaces. Sorry. Questions?
Okay, if not, we will have 2 months to ask questions to the speaker. So let's thank the speaker again. As you probably know, there is the